In this video, we're going to learn about bond and molecular polarity. So you might recall that we learned about electronegativity before, and we were able to look at electronegativity differences to determine whether a compound is covalent or ionic. And then among covalent, there was the question of polarity, like how polar of a covalent bond are we considering? In the case of F2, we've got two fluorine atoms with electronegativity that's equal. So 4.0 for one fluorine atom minus 4.0 for the other equals 0. And that indicates that we have no polarity. It's not that one atom is pulling electrons closer to it than the other. In the case of HF, well, the fluorine is 4.0, but the hydrogen is 2.1. And so the difference is 1.9. So we have a very, very polar covalent bond where the fluorine is partially negative because it's the more electronegative element, and the hydrogen is partially positive because the electrons are not really staying towards it. In the case of lithium fluoride, this is something where if you were to check the electronegativity difference, it would be even greater. But simply put, a metal lithium with the nonmetal fluorine indicates that you have an ionic bond. This isn't what we're talking about right now. We're talking about covalent compounds. So a bond is polar if it has a dipole moment. And what is a dipole moment? How do we signify this? Well, if we look at F2, there is no dipole. But with HF, there is. We know that we can draw the Lewis structure of HF as such. I am taking a little bit of a shortcut here to get to the Lewis structure. But the dipole moment we can draw in, and I'm going to draw it in red. So we always have the dipole moment pointing in the direction of the more electronegative element, and we put that little line there. So that arrow with a line here indicates that there is a dipole moment. And you're not going to have to quantify it, but you will need to understand that what this means is that the fluorine is a partial negative, that thing that looks like almost like a D, but not. That's a lowercase delta in Greek. And delta negative and delta positive mean partial negative and partial positive. A full positive and negative would be in the case of lithium fluoride, where the lithium is fully positive and the fluoride is fully negative. But because this is a covalent compound and there hasn't been a full-on transfer of electrons, we indicate partial positive and negative and a covalent bond. So let's consider, though, carbon dioxide. All right, so if we look at CO2, we're going to have carbon with an electronegativity difference of 2.5, oxygen with 3.5, and the other oxygen with 3.5 as well. So here we can see that there's an electronegativity difference in both cases. And so both of these bonds are polar. So we would have to draw the bond dipole moments always with the arrow pointing towards the more electronegative atom, meaning the atom that is going to be partially negative. So we've got a dipole moment in one direction, and we've got a dipole moment in the other direction. And if you want to say, where's the negativity? We've got a partial negative here, a partial negative here, and a partial positive here. But carbon dioxide, actually overall, as a molecule, it is nonpolar. So the bonds are polar, and you can tell, you can see in the electronegativity difference. But how do we get to molecular polarity? We look for symmetry. In this case, you have a dipole moment in one direction, and you have a dipole moment of equal magnitude in the exact opposite direction, and they'll cancel each other out. So as a result, we have an overall no net dipole moment. Net meaning when you add all the bond dipoles together, whatever the result of that would be. But in this case, we have no net dipole moment. Now consider water by contrast. Water, you guys probably already know that water is polar from your studies of biology. And we can figure this out based on the fact that oxygen to hydrogen, well, we've got 3.5 as our electronegativity. 3.5 minus 2.1, that equals 1.4. This is a significantly polar bond in each case. And so if we're showing the dipole moment, we're going to show it like this, and we're going to show it like this. So these are the bond dipoles. And you can say that the hydrogens are partial positive, the other hydrogen is partial positive, the oxygen is definitely partial negative. But when I add these two together, when I take the one on the left and the one on the right, these two, they point overall towards the oxygen, but one is kind of going right and the other one's kind of going left. The right and the left end up canceling each other out. And so our net dipole moment, I'm going to draw in green, and the net dipole moment is this. So this is our net dipole moment. And if you ever, well, when you take physics, you'll learn about vectors, and in math, you may learn about vectors too, where you're basically adding this vector and getting a resultant when you add these two different dipole moments together. The resultant will include not just the magnitude, but also the direction. And the direction here, though, I think is fairly intuitive. The right and the left give you an overall net dipole moment going in this direction. So it is important, guys, that you always draw water to make it look like it's polar. And by that, I mean you should draw it where this is looking angular. It looks like you've got hydrogens on one side and lone pairs on the other. You may want to draw it, in fact, I'm going to draw this in red and put an X through it when I'm done. You may want to draw it like this because it looks more aesthetically appealing. But the problem here is that although this would be actually, if you were to take this three-dimensional molecule and rotate it in space, you could tip it in a way that it does look like this kind of, where the hydrogens are kind of pointing away from you into the screen and the lone pairs are coming up and out at you. But you know what? This looks too nonpolar. The appearance is too nonpolar, and it will be confusing and misleading to you and to anybody who's reading your work. So never, ever, ever draw water like this when you know that water is polar. So our Lewis structure is best represented like this, so that you can see the polarity. And I'm not going to show the work, but I will show the net dipole moment is going in that direction. So I hope this video has helped. Let me know if you have any questions or comments in the comment section below. Thank you.